the mean value theorem. We're going to look at two mean value theorems. The first one here is a review, the mean value theorem for derivatives. This one should be a review. The idea for this yellow function f of x, the idea is that the average rate of change is equal to the slope of the line connecting the endpoints. So the slope here, m, equals the average rate of change in f over a to b. And the mean value theorem says there must be some x value between a and b such that the instantaneous rate of change is equal to the average rate of change. So the slope of some tangent, try my best there to make that tangent, the slope of some tangent, we'll call that f prime at some value, x value c, and the slope of that tangent will equal the slope of the line connecting the endpoints. And this is a guarantee theorem. It guarantees that as long as this yellow function f is continuous on the closed interval and differentiable on the open interval, it guarantees we're going to find an x value between a and b such that f prime of c equals the average rate of change. And now we're going to look at the mean value theorem for integrals. This one is going to be new. In the function we have below, similar function as the one before, this time the average value would be the integral over the interval. And if you recall, that's the average y value. So we have small y value, larger, 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 larger. Each one of these dots represents a y value. And then the function will have an average of those heights, if you will, or average y value. And it's the integral over the interval. And the mean value theorem for integrals guarantees that there's going to be some value, we'll call it z, between a and b, some value that equals the average y value. So if I compute the average y value, let's say the average y value is somewhere about here in that blue color, then I can see that there is a value x, namely x equals z, such that f at z equals that average value. The first example, y equals 3x squared minus 3 on the interval 0 to 2, that graph can be seen below. Part A wants us to compute the average rate of change. I'm going to come over here and call y equal to f of x because I prefer to use f of x notation when computing the average. So the average rate of change is going to be f of 2 minus f of 0. Again, the slope of the line connecting the endpoints, that's change in y, over change in x, which is 2 minus 0. If I plug that in, I'm going to get 9 minus a negative 3 all over 2, and my average rate of change will be 12 over 2, or simply 6. In part B, we want to find the value of x that satisfies the conclusion to the mean value theorem. So I'm going to compute f prime of x, and f prime of x is 6x, and that's it. And we have to see where 6x will equal the average rate of change. So we want to find where 6x will equal 6, and that certainly will yield x equals 1. The question also wants you to illustrate this graphically. I'll draw my average rate of change by trying my best to do a straight line connecting the endpoints. Okay, it's about as best I'm getting. There we go. And the slope of that line is the average rate of change. And then we found that at x equals 1, the instantaneous rate of change will also equal 6. F prime at 1. But the actual answer to the question is for what x value, and that x value is x equals 1. Part C wants us to find the average value of f on the interval 0 to 2. So that's going to be integral over interval. And we're going to do, let's do this by hand. First, let me write it like this, because this is how it's often presented. So I have 1/2. I'm going to take the antiderivative, and the antiderivative is x cubed minus 3x, and I will evaluate that from 0 to 2. So I have 1/2 times, I'm going to plug in the 3, so I'm going to get 8 minus 6. And then I'm going to subtract, I'm going to plug in the 0, 0 minus 0, and so this will come out to be 2, and then over 2, which comes out to be 1. The average height, or the average value, is equal to 1. In part D, we have to find the x value such that f at some value of x will equal 1. So we want f of x, which equals our original 3x squared minus 3, to equal the average value. We want 3x squared minus 3 to equal the 1. Solving this, 3x squared equals 4. Coming over here, we have x squared equals 4/3. And then this should yield 2 answers, but we're only looking on the interval from 0 to 2. So the only thing we want is the positive root 4/3, or we might write 2 over radical 3. Now this is a calculator question, so if you want to get a decimal feeling for this, it comes out to be approximately 1.155. Now we have to illustrate this graphically. The average value is 1, and we have to find the x value where that happens, and we calculate it to be 1.155. And so I'm going to mark that x value here to be x equals 1.155. Right there. Example number 2, the function f of x is seen here, x cubed over 2 plus 2/2 x squared minus 3x minus 4, and that is on the interval -4 to 1. Question A wants us to find the average rate change, and the average rate of change will be f of 1 minus f of -4 all over 1 minus a -4. So that will come out to be, when I plug those values in, -5/5. The average rate of change is -1. Now we're question B. To find the value of x that satisfies the conclusion to the mean value theorem. Alright, so I'm going to find where f prime of x equals average rate change. So my f prime of x is going to be 3x squared over 2 plus 3x minus 3, and that has to equal the average rate of change of -1. So now it's ready. It is time to solve this. This is calculator active, and the answers won't come out pretty. So what I'm going to do is say 3x squared over 2 plus 3x. Then I'm going to add 1 to both sides to get -2 equals 0. Now I have to solve this. What I'm going to do is graph this here as y1 and find the 0, or possibly zeros. See, the mean value theorem for derivatives guarantees there's going to be some value of x between -4 and 1, but there could be more than 1. The guarantee is that there is at least 1, but there could be more than 1. So take a moment, graph this here as y1 in your calculator, find the 0 or zeros, and we'll show this graphically. In my calculator, when I graphed this, it was a parabola, and the parabola came down like this, intersected. I found these zeros here and here using the zero function in the calculator. And those x values come out to be x equals negative 2.528 or x equals 0.528. It is time to illustrate this graphically. Our average rate of change, slope of the line connecting the endpoints. So we go like that. M equals negative 1. Average rate of change. And you can even see from this graph that there's going to be two solutions. And we found those two solutions to be at negative 2.5-ish. So negative 2.5-ish here. The slope of that tangent is parallel to the slope of the line connecting the endpoints and also at 0.5-ish. So we have it here. The answer to the question, there are two answers to the question. Both of these answers are inside the interval -4 to 1. Suppose one of the answers were actually -4, which it is not, but that would not get included because the answers we seek are the ones inside the interval, not endpoints. Part C, the average value. Average value of f of x is going to be the integral over the interval. You can go ahead and use your calculator if you'd like, and that's going to come out to be 3.125 divided by 5, and that answer comes out to be 0.625. Now in part D, we want to find where f of x will equal the average value. We're finding which values of x this occurs for, and our f of x is x cubed over 2 plus 3/2 x squared minus 3x minus 4, and we're going to set that equal to the average value, 0.625. So there are two ways to do this. You could graph your original function f of x together with the average value constant at 0.6, and you'll see, try to make that as straight as possible, and you should see from that that there will be two values of x that will satisfy the conclusion, because two values of x will have f equal to the average. So you could graph them both and find the intersection, but I find it to be a little easier to write this as x cubed over 2 plus 3/2 x squared minus 3x minus 4. Make a new function that subtracts the 0.625 so that I can set it equal to 0. I find it easier to find zeros than I do to find points of intersection. So if I change this now to be maybe y2 or y1, whatever, but it's a new function because it subtracts the 0.625, and I find it easier to find the zeros. At any rate, you should find that the values of x that satisfy the conclusion, -3.928 or x equals -1.139. So again, these guarantee theorems, such as the mean value theorem, guarantee at least one. In this case, both the mean value theorem for derivatives and the mean value theorem for integrals both yielded 2 answers. There could be 4, 5, 6 answers. Guarantees at least one.